This is the video for the collision system. So collidable inherits from GameObject. We have our big four. We have our submit registration and deregistration commands, which go through our brokers. We have our call for collision. Collision is the overloaded function that the user will override for when a collision occurs. We have this function that will get our B-sphere, since our collidable holds a B-sphere, an ABB, and an OBB. Currently we only have the B-sphere, so that's the only function that is currently written. We have the ability to set our collider model when we after we created our game object. This will allow us to accurately create our B-sphere. We can update our collision data for when an object moves. I've implemented multiple ways of utilizing the system. This last one would have been the system that was originally intended by you, Andre, which was just to pass in a world matrix, deconstruct the matrix for the scale and the current position. But as I mentioned multiple times, I thought that system was rather costly. So rather, the user, in this current case, can pass in the current world matrix or the current position of the object. I can deconstruct this simply for the current translation vector, and since I know, the current position. After I have that position, I'll be able to use the scale factor being this constant float and create the B-sphere to a more accurate size and representation. And like I said, this would be a much faster way than constantly deconstructing a matrix every time the given object updates, because this would be an entire call every single time a model moves, and a model can move, and multiple models can move throughout the scene at any given update cycle. The very last thing we have is our registration and deregistration commands, because we don't want those to go to waste when they've already been created. We have our current state, we have our collidable object pointer, and we also have a pointer for our model for reference. Collidable base is merely an empty base class to offset all the weird things that happen when you try and store things in containers that are templatized. Going into our registration and deregistration, all it basically does is once we go through our command pattern, we execute, and when we execute, we go into our collidable group, our templatized collidable group, and we register that given pointer or deregister it from the group. Going into the group very quickly, our collidable group once again has a collidable group base in order to offset a lot of the things that happen. The container of our collidable group, first and foremost, is a set, and I define that collections iter to be right here. The iterator is basically used for the quick removal from the set. We have our public API to register and deregister and get the current collection. This will in turn be used for our test later on. We make sure that things are properly deleted when need be. This is our instance creator for our singleton. Moving further on, our quick removal. I do have a map for quick removal. So when the when our collidable base is passed through our map for quick remove, we will store the iterator for quick removal in that map. So our process for adding something to a set is, I believe, log n, and to iterate and to retrieve something from a map is the equivalent. It's log time. So after we've inserted, we add it to this map, so we can quickly remove something in roughly, I believe it's log n time. I don't believe that accessing from a map is constant time, but this was the best way that I knew how to implement this this quick remove. Once again, it's a map where we have our collidable and we have our collection iter, so we can quickly remove when we need to from the from our collidable group. Our collidable manager, once again, will process our elements when needed, and it will execute when need be again. We have our collidable group, and we have our iterator at the end, so when we insert something, it's always at the end of our list. Going further down, we make sure we delete everything. Our debug messages make sure that at the very end our collidable group is emptied out. Going into our templates, when we set our collision pairs, these functions are called from the scene. So we register these pairs and we insert it into our list to be called. We also have one for self that is also inserted into the list. And when we remove, since we have saved that iter inside our scene, we can quickly remove in constant time from our list. Going into our pair works by grabbing a reference from our collidable groups given our two templated types, and when we go through our process elements, we go into all of our executes, both for the pair and self. And pair, for this case, will iterate through the first collection, and then iterate through the second collection, get our B-spheres, check for our intersection, and in the process, after we've checked for those specific B-sphere intersections, we will register the collision, and our B-sphere will call render B-sphere on red, which gets added to the visualizer's list to be executed on the next draw cycle. If not, it will just, again, go through our list for our visualizer to be executed on the draw cycle, and it will just be blue. That should cover everything for collision. For the most part, I believe the entire collision system should be in big O log n time. I haven't found a way to make it constant time yet, but that might just be a little bit more to work on.